Jeremy's he's away, so he wanted this to be recorded so we could hear it. And Todd Harmon as well. We'll record this for him too.
Hello.
So that'll be good for them to see this. So I'll just kind of fill you in on what I've done since I think we had a conversation on email about efficiency. And at the time I was doing about 4.1 million steps per second. And so everyone knows that's through the domain. One step is from one cell to an adjacent cell. And then of course I'm keeping track of a few things: attenuation, volumetric emission, and some reflections are going on as well in the domain. And also, I think at the time I was talking to you, I was just sort of chasing these rays around. Well, I've been able to add the physics in so that I can do something meaningful with those rays. So now I can actually compute the radiative flux divergence for every cell in the domain.
Okay. And this is all within the UCF.
Yeah.
So that's the context.
The really good news is that while I've been adding more physics, I've also been incorporating these little computer science tricks to speed up the efficiency. And so even though there's a lot more going on, I actually can do more steps per second now. I'm up to about 7.6 million steps per second.
Okay.
And I think your benchmark that I'm shooting for in an ideal situation is about 10.
Yeah,
Plus or minus, you know.
I think you should be able to get at least 10.
At least 10, okay.
But so one of the problems with a lot of architectures these days is it takes an exponentially increasing amount of heroics to go beyond. So yeah, I mean I think that's a reasonable place to start.
Okay.
There's and this is per core.
This is per core.
And have you tried seeing what it is on multiple cores?
Not yet.
That's this.
That's
purpose
that's
of
the
this
purpose of
meeting.
of this.
That's why you're here.
And
To set your expectations, it will go down. The question is how much. So I would, and because right now you have the benefit of a large cache relative, for just one core.
Right.
And if you now are doing 4 at a time, or 8 at a time, or whatever you have, you essentially have 1/4 or 1/8 of the cache for each one of those fields. So
okay.
so it
Unless we can reduce the memory footprint, right?
hang on just a second. I gotta count for you. Hello? Hi. Okay. 11 o'clock today. Yeah. Do you think I could have till 11:15? Okay. Yeah, I'm actually off campus, so I don't have access to any of my stuff. I don't have access to my computer right now. So that's, I could make something up, or I could do it scientifically by 11:15. Okay, thanks. All right.
You've got to go.
No, I don't. It is 11:15 California time.
Oh,
so
that's
So you have an hour and 14 minutes.
So I'll need to leave here by in an hour.
Okay. Well, let's make use of our time then. So this is the most important thing. I have other things on my slides that we can look at, but the most important thing is how are we going to efficiently get this thing to run in parallel?
Yep.
Yeah, because I have some images, yay, images of the radiative flux divergence, and different ways to get the accuracy better.
And these are
So this
noisy
is
just because of Monte Carlo, right? It's
noise because of
homogeneous
Monte Carlo.
domain.
That's right. And here's the discrete ordinates method results. You can see how smooth they are, and so there are a couple things that I did to try and get it more smooth. You can see I increased the number of rays per cell. This is a 50 cube domain, a slice. it's an XY slice halfway through up in the Z direction. Okay, so we can increase the number of cells, and you can see that helps. But what I found actually that did an even better job was averaging, taking the same time step, running it twice and averaging them. And so here's an average of 2, and here's an average of 5, only with 1,000 rays per cell. And you can see it's significantly better than 15,000 rays per cell. So we can get better results with essentially 1/3 of the computational time.
So something's fishy with that. So
No, the 5 average with 1,000.
so you take 2 independent runs
2 independent runs
and average them.
And because they're Monte Carlo, each the deviation from the true value at any given cell, the probability that it's high one time is the same that it's low the next time. So when we average things out.
But I don't understand how mathematically that's any different than
I know, than just doing more rates.
So there are a number of things. So if you're getting the fact that it's different, then something's wrong.
Something's wrong.
So,
Yeah.
so let's figure out the things that could be wrong.
Okay.
Right.
Yes,
So,
yeah.
so what random number generator are you using?
Mersenne twister.
Okay. And how do you see it?
How do I see it?
Seeded.
Oh, how do I seed it? It's auto seeding right now, so it might start at the same seed every time.
Okay. So that's even fishier, because in that case,
Then it would be
would
the same.
be the same. You would get the same thing twice in a row, right?
How is it being seeded?
I mean, I guess if it's auto seeded once and then you pick up from that sequence, then it.
we can take a look at it because I'm not sure how it gets seeded.
So if you're not doing if you're not consciously seeding it,
I'm not.
then it's just, it'll pick a default seed, which is usually fine. It's
Okay.
not going to be fine when you want to do it in parallel.
Okay.
And the reason is for your own sanity, you're going to want to make sure that the answers are the same when you run it on 2 cores or 4 cores.
Okay.
Right. Otherwise, the answers are going to be a little bit off, and then you're going to sit there scratching your head wondering whether you have a bug or whether it's just Monte Carlo.
Okay.
Okay.
So you're saying when I run things with 2 cores, when I run things with 4 cores, I should specify a seed, so I should have identical results just to make while I'm debugging?
So so if you run it, so let's suppose we take a domain, and so a seed in Mersenne twister is an evolution of some internal state.
Okay.
Right. And so there's some sequence that you could think of as just counting. It's just in some wacky tangled space, right?
Okay.
And so if you do that in this domain, you do all the ones in this cell, you do all the ones in this cell, you do all the ones in this cell, you will get a different answer, ignoring multiple cores. That you will get a different answer than if you did it in this order, and then came back and did these. Right? So these first 4 would be the same, but everything else is going to be a completely different random number stream.
Okay.
Is what it's usually referred to as.
Okay.
So, and so just changing the ordering of it can lead to differences. They're still both equally wrong, right? I mean, they're both equally valid in terms of they're both reasonable Monte Carlo samples, assuming everything else is right. But if you so one way, so now if you wanted to go to something to avoid that, what you would need to do is ensure that the same stream is used, the same sequence is used everywhere.
Okay.
And the only way to do that would be to generate all of them in advance, with some serial process, and then farm out half of them to one core and farm out half of them to the other core.
Okay.
And that's just not tractable. It's too much storage, too much, way too slow, and just not reasonable.
Okay.
So what people typically do is is seed the random number based on some atomic unit, like per cell.
Okay, yeah.
You set the seed based on the cell itself, and usually you throw away a couple, the first couple random numbers. I don't know how well Mersenne does it at reseeding, but if you take you set the seed based on I times, a million, or 6 plus J or something, plus times 1, 3 plus K. So in that case, no matter where you start, no matter what order you do this in, the seed, when you start working on that particular cell, will generate the same stream.
Okay.
And then it's just infinitely easier to track down bugs
Sure,
and to make
sure.
sure that your answers are consistent.
Okay. I can dig into that to see how to see that. And I think, Paula knows how to do this. Paula mentioned doing something like this.
Yeah. So the only gotcha with Mersenne twisters, Mersenne generates random numbers in bulk. So,
Okay.
so the way it works internally, it doesn't generate one random number at a time. It generates like 1,000 random numbers at a time.
A series.
And so if you're doing this, it might be inefficient for small numbers of arrays in the cell, because you're generating 1,000 random numbers and only using 10 of them or something, right? But that's that can be managed in a number of ways, like doing it for groups of cells or other things like that. But and so I wouldn't. You don't need to worry about that right now. Just be prepared for that result. when it
Okay.
comes.
If it's inefficient, do group
Yeah.
generate
We
a
can
series
talk
of
about
groups
other
of stuff.
ideas of how to handle that, or maybe even different random number generators. That,
Okay.
There's alternative implementations of Mersenne that don't have this psychosis.
Okay. Okay. I also have a question on the same topic of parallelization.
Yep.
Because we have a choice in how we parallelize. We can parallelize by patch, we can parallelize by cell, we can parallelize by ray. And I think from what I've read in the literature, I think the way to go is to parallelize, by cell, but by handing the information about the entire domain to every patch, so that we're not having to hand off information of thousands of cells, millions of cells, as soon as they leave the patch boundary. I think the best way to do this is to allow each processor, each core, to be able to trace these rays through the entire domain.
And that'll work really well until about 16 processors. And then the all-to-all communication, so if you're running it on 1,000 processors and they all have to have a copy of the entire domain, you're only going to be limited to very small domains.
Yes.
Because they're just not going to fit,
Right.
or it's going to be arbitrarily expensive to just make sure that everybody gets a copy of every
Yes.
other data. And so that is a good place to start. It's certainly not going to get you to 1,000, 1,000, 10,000, 100,000 cores.
Okay.
There are, the reason this is, you get a PhD at the end of this. It's not easy there isn't a good answer, a simple answer.
Okay.
There's basically three. So let's suppose we want to so we have that part working. Let's suppose we want to now go to the next step where we want to find a way to make it scalable. And there's basically three ways that I can think of doing it.
Okay.
There's two typical ways, and then there's a way that I've talked about for 10 years that has never been tried to my knowledge.
Really?
So the typical way would be to like you said, parallelize, or to have a strict domain decomposition. And if a ray leaves a patch, you hand off that ray to a neighboring processing element. That's not as straightforward as I would like it to be in Uinta. It could be made to work. Getting it to be efficient is probably going to take a little bit more head scratching and thinking about it. Probably the most reasonable way to do it would be to actually ignore Uinta for that step and actually just use MPI directly, which is what we do for some of the numerical solvers and everything.
Okay.
And so you set up what's called a game schedule task, and it runs them all at the same time, and then you can do some fine-grained communication to hand off rays. And so, of course, with the Monte Carlo technique. Well, okay. So let me get. We'll come back to that.
Okay.
As we segue into the third piece.
Okay.
So the second way to do this is to actually keep all the rays on one processing element, but drag data over only as you need it.
Okay.
So if it's an optically thick medium, most of the rays are going to not wander very far. Right? They're going to scatter locally and not stray very very far away. That's what makes it look dark. Right?
Yes.
And so so what you can do is you can rely on that assumption and say, well, I'm going to work on the patch that I own, but if I need something else, I'm going to go and request it. Right? And then I'll send a message to a neighboring, to wherever it is, request that data, and work on that. And then if I run out of memory, I might have to throw some of these away, and then go back and get them later. Get them again later.
Because eventually, we're doing so many rays per cell. Eventually, we're going to end up requesting all the other patches.
Yeah, you won't.
But we do it one at a time,
Yeah.
so that we can fit it on memory.
Yeah. And typically, a good strategy would be that you use half of your local memory for the domain that you own,
Okay.
and then the other half for domains that are sometimes 1/4 and 3/4.
Okay.
Some small fraction for the domain that you own, and then 3/4 of it is just a cache for the neighboring processors, and so you drag data over as you need it.
Mm.
So that one works really well for optically thick media. 'Cause like
Okay.
I said, most of it is not going to wander outside of a very small window. If it's truly just a big thick black cloud, you'll probably wander into the 26 neighbors and never any further, or rarely any further.
Right.
But if we return back to the first technique, which is
Pass off every ray.
it actually works better for optically thin media, because what happens is, let's suppose we have this domain, and we're doing something with a heavy scattering load, and so what will happen is the ray comes over here, and the next time, next step or a step or two later, it's going to come back.
Yeah.
Right?
Yeah.
And so it's going to cross this over and over and over again. So if every single time that requires a message across some computer network, then that messaging can dominate the cost. Whereas if it's an optically thin media and it largely goes straight, then it's painful, but it's not. Its communication time can be made small compared to the competition.
I see.
So one way to fix that, as we try to drive to what the third idea is. So one way to fix that would be to use something like the ghost cell infrastructure in Uinta. And instead of having a strict boundary, you have some sort of a hysteresis type thing. So what you do is this.
Video here.
Uh,
Video.
this domain extends, has some redundant, so this processor has some redundant data from the one on the right,
Okay.
and this processor has some redundant data from the one on the left.
Okay.
And so now, as you walk through this, all of these steps don't actually ever need to leave that domain, and only eventually maybe it does cross that domain, and there's one message, but then it can wander a fair ways off without triggering another message sent.
Interesting.
And
okay.
so that you can think of as a continuum between the strict domain decomposition and what you've described, right? By simply varying the amount of repeated data, right? The one you described where you repeat everything everywhere is simply that
The limit.
technique
yeah.
in the limit.
Okay.
And so, now a variant of that idea that would be likely to be highly publishable is to actually use another observation, which is that something that is far away is blurry, right? From a radiation transport point of view.
Yes.
If you have any sort of scattering or absorption going on,
yeah.
it's blurry. And so you don't, something that's way out here, you don't need it to be as resolved as the one that is right next
Sure.
to the container.
Sure.
And so the idea is to use, you could think of it as, well, I'm, in my domain, I'm going to have, the full level of detail, and then it's going to fall off. Maybe I have a half resolution version for a while, and then a quarter resolution version for a while.
Ah.
And so then you do have the whole domain, but you don't have a full copy of the data, right? It tapers
Right.
off.
So you can fit
That's
it on
good.
memory.
So you can fit it in memory, you can manage it computationally.
Yeah.
And it's a little bit like, so you could do this pretty easily for regular domains, but it's a little bit like a corruption of the AMR infrastructure, where the
Yes.
AMR has nested
Yes.
patches, but that structure is global for everybody. Right? Everybody has that same structure.
Okay.
But you could use the same AMR infrastructure where, locally I have my AMR view of the world, and it might be different than my neighbor's AMR view of the world, but both of them are tuned, are the right approximation
Yes.
given the constraints. And so that is a technique that I think could be used quite easily to get these types of things to scale without.
Because
Without affecting accuracy.
And the infrastructure's already in the UCF for that, is your point. How much?
Some
Infrastructure
level,
is
some
yeah,
level.
80% there.
This is where Todd comes in.
Yeah.
That is a great idea.
That is because the farther you get away from where you're emitting your rays, the less those regions contribute to the incoming intensity.
It's not only that, it's that the intensity is a function of the solid angle. And when
Right.
we're talking about spatially, the solid angle grows for the same solid angle.
That's right.
The further away you are, that covers larger space.
Yes.
The nearer you are, that covers smaller space. And the
Yes.
intensity is a direct function of solid angle.
Yes.
So you get the same accuracy.
Right.
Yeah, we don't need to track the details of the sunspots on the sun to know how
Right.
hot it is outside, right?
Right.
It's just-
Yeah, and where it's most.
But you need to know the clouds locally around you.
That's right.
Exactly.
So we get the best of both worlds. Yeah. Okay.
So that I'll be honest, it is going to be a little bit of an uphill climb to figure out how to do that in Uinta. It's not something it's something that where a lot of the pieces are there, but it's not something that I can just say, oh look, go follow this thing and it'll happen, right?
But Isaac's not alone on this one. So we've given some money to Todd to
Yeah.
help us And Todd would be perfect to help us with this kind of AMR structure in the background, so
Yeah.
that Todd can deal with it. So we can parse these pieces out in the UCF
Yeah.
to make this happen. Isn't this what we want to do? This is your 10-year mission, isn't that the one you, isn't that? Okay, so it's time to deliver.
Okay. Okay.
So we were thinking, I think Isaac and I have talked about, I wanted to bounce two ideas off you. One is a stripped down version of what you talked about here,
Mhm.
where if you have the arches computation and if you coarsen that by a factor of 4 in each direction,
Yep.
pretty soon you can put that in cache, in
Sure.
memory,
Yeah, right.
in memory,
Yep.
and you can copy the whole domain. So in using the AMR infrastructure, that could be pretty easily
Sure.
done where radiation's done on a coarse mesh. So coupling that with, right now, radiation's done periodically in time, but it's done in lockstep with arches. In other words,
Sure.
arches finishes a time step, radiation goes,
Yeah.
then arches picks up for a few time steps, then radiation goes. But there's no reason that because
Yeah,
it's
it's
segregated,
synchronous.
yeah, that's right. So the radiation takes a snapshot of the field from arches. Arches keeps going, radiation goes, and when it's completed, they sync again, and then so they're completely asynchronous, and that buys you a whole lot more scalability because now arches can be running on. Well, you spread the problem across
Sure.
2 subsets of the computer domain.
Yeah, you don't have to be limited by the compute time of the radiation, which is which is restricting us now.
Right. Yeah. So I think getting a real segregated solve in place will help a lot with the efficiency, and doing some kind of AMR will help with the scalability.
Yep.
Are you saying dedicate some of the cores, some of the machines to doing radiation all the time?
Right.
And some of the machines to doing arches stuff all the time?
Right.
And they share
And
information
then they
every
just sync periodically.
yeah.
Like when the radiation's done, it
Right.
just says, okay, I'm ready
Take
to
it.
do more, right?
Okay.
And they sync. And that would allow a lot more, it would allow us to spread the computation a lot better across the machine.
Sure. Sure.
And if radiation only scales to 100 cores, but arches scales to 10,000, then you can still use both of those
That's right.
effectively. And
So we should get back to the why the answers are wrong in a second. 'Cause I
Yes.
think we only got to one
Yes.
slide.
Yes.
But the it would be good. You should also read Vincent Pereira's paper on sequential Monte Carlo, because so typically for these types of problems, Monte Carlo has a convergence rate of 1/n squared.
Okay.
Right. So to get an answer that's twice as good, you need 4 times as much work, 4 times as many arrays, which might be actually more than twice as much work.
Right.
So Vincent actually has some techniques that actually reduce the order of convergence. And so for a large number of arrays, it can pay off big time. And the way he does it is by using a data structure to track an approximation of the sort of the current best answer at any given position in space, and then he uses that to drive an importance sampling process, and and then also a variation diminishing. So basically you are so importance sampling you can think of as dividing a PDF, and variation diminishing you can think of as subtracting a PDF. So actually by combining both of those techniques, which have really never been done before, you can actually improve not only by a constant factor, but by actually increasing the order of convergence rather significantly. And so that's it's not going to help with scalability because it's not going to hurt you either. It's just not going to help. But it's something that I think would be relatively straightforward to adapt to this domain.
Okay.
So
Okay. I'll get that paper.
if you have a hard time finding it, let me know.
Okay.
If you just type sequential Monte Carlo and Pegoraro, you get it. But,
Okay. I have a question of something, and it involves piecing together the information so that we can hand off the flux divergence of the entire domain at the end. So once we've done, so if we get this working, this sort of AMR type idea,
Yep.
so each core is working on solving for the flux divergence of a subset of the domain.
Right.
And so it has solutions to the flux divergence for those cells.
For a patch. Yep.
For a patch. What's the best way to save that information and to, at the end, hand that information off?
So UCF kind of does it for you automatically.
Does it?
So if you just, you tell it, I have this domain, and it'll tell you, okay, I'd like you to work on this patch. Right? And then you simply, loop over the cells in that patch and write the data in that array. And then that can subsequently get broadcast to wherever it needs to be based on what things downstream have requested.
Okay.
And that doesn't change in the AMR world, because all of those blurry versions of it are read-only, right? They're not stuff that you're actually doing any computation on. It's just stuff that you're using to compute the data on that patch.
Okay. That's good to know that you went to set up to handle that kind of thing.
But do you have any thoughts on getting this to go not just the MPI parallel, but the multi-core? Because we're going to have to basically do that independent of Uinta, at least at some level.
So if you're trying to do it with multiple cores, you're probably best off either using OpenMP or just some very simple get
Boost
I'll
thread.
write Justin lunch or something. He can show you how to do P threads or something.
Yeah.
But it's if you do it either with explicit threads using P threads, which is pretty straightforward, on a single for this type of thing on a single machine, or with OpenMP, you'll on a single node, you don't have all of these headaches about I can't fit it, and things like that, right? Because they all have the same memory visible, and so you just have a single copy of the domain. You have a single copy of the output, and then you divide up the cores and have them each work on a region of that domain. The only gotcha there is you want to make sure that you divide it in the courses dimension. So which in Uinta is actually Fortran order. So the K dimension is the coarsest.
Okay.
Is the elements of K are the furthest away in memory as you increment K, whereas I is the
Okay.
Now, so that works when you're, and you're going to parallelize by RAID then, right? Or you're
Or by cell.
Or by cell.
Yeah, I mean, actually, on a single node, doing it by array doesn't make any sense. I mean, handing off arrays between nodes just doesn't help. That's a big. So when I say parallelized by array, I'm talking.
I'm talking about within a node, on a single
Right, so
computational
within a node.
across cores.
So you can, so there's two different dimensions here, and I think we're talking about different slices of the space. So one is what is the unit of parallelism,
Mm-hmm.
right? So and so what I'm recommending is that you, Fortran order is like this, right? Is that you just slice up the domain in one dimension, and for 16 cores, even if you have only 50 cells, there's still a fairly equal amount of work between those different cores. Another way, you could also do it in 2 dimensions and get slightly better, slightly less susceptibility to integer round-off errors.
And
When you do 50 cells on 16, some of them are going to have 3 and a couple of them are going to have 4.
Yeah.
But I don't think that there's any, unless you have some exotic SGI with a 4,000 processor or 4,000 cores on a single shared memory device, you're unlikely to need to go any finer than that, like to be parallel over the rays within a single cell. And I
Now,
also
your
don't-
outer loop is over rays, right? And then it's over cells. Is that
No,
Cells
cells then
then
rays.
cells.
cells then rays? Oh,
Yeah.
okay. Okay. So that now I understand what you're suggesting.
Right.
Okay.
Yeah, that's definitely the right way to.
Yeah.
Okay. In fact, if I'm getting close to this benchmark, this may not be necessary in terms of millions of steps per second per core. And this is kind of a lot to ask, so it's okay if this is unreasonable, but I would be interested for you to look through my code
Yep.
to see if you can find some sort of obvious, novice mistakes I'm making in terms of efficiency.
Yep.
If he wants to get from the 6.5 to the US, he's got to hit the 10.
That's right. We want to hit 10, so so I'll send a copy.
I'm pretty sure on the GPU we can get actually hundreds of
Ooh.
ones.
That would be fantastic.
And that other, I was actually trying to do the math in the back of my head for something else. But the other technique that paper I sent you that is probably going to stump you for a while because it's not the easiest paper reading for people that have been doing this for a long time. But it doesn't march through the domain.
Okay.
It what it does is it computes a scattering length and then immediately jumps to that point. Or actually what it does is it computes a scattering length, but instead of jumping to that point, it computes an appropriately distributed random number that will jump somewhere between there and that length. And so that's what makes it unbiased, is that it will randomly sample that scattering length. Sometimes it won't scatter, sometimes it will, and as long as you can bound the maximum density in the domain, which you can, right? You know where the densest location is, then you can apply this technique. It was actually some paper that was written a long time ago on kind of stuff behind a file cabinet. Nobody has really picked up on it as much, but Pete Shirley has an implementation of it in Galileo, which is an open source ray tracing system. And so the reason I'm mentioning this is that it can, if you have high variations in optical thickness, right? You have a lot of really fine areas and some areas where there's no scattering. The ray marching techniques kind of stumble because what they do is you have to set the marching interval fairly small to get the thick media correct, and then they have to walk long distances to cover the thin ones. And this technique handles that fairly gracefully.
Okay.
And you don't have any of the marching business. You just say, what is the value at that point? And then it jumps somewhere else and say, what is the value at that point?
Okay.
And it jumps somewhere else. And probabilistically, it samples things closer for optically thick media and further away for optically thin media. And that is also likely to be far more efficient because you're touching a lot less data per amount of information that you're capturing, right? So per sample, even though it's Monte Carlo, so now you've got another dimension of averaging. There's still a lot more information that you're gathering because when you're stepping along, you know, if you have to step through 10 or 20 cells, there's a lot of work that you're doing
Yes.
without actually contributing any data to the final answer.
Except for one thing, and that's volumetric emission. Because it's
So this will handle
participating.
emission too. You might have to figure out how to work it
Okay.
into the domain, but it should handle volumetric emission.
So if it knows where to go until it scatters, it can get the information about the cells in between, because every cell.
So it might skip over them, but sometimes it won't. So, right, that's the whole point of Monte Carlo is that
It's
you know,
probabilistic.
it all works out in the end. So,
Right.
So,
I just don't quite see how it's getting, because every cell in between, you know, if the ray's here and then it's here, every cell in between there on that ray is contributing back because we're doing reverse Monte Carlo. It's emitting
sure,
back.
but the point is, well, and that's, you're still doing reverse Monte Carlo in the end, right? So,
Okay.
so if you jump from point A to point B, you're right. There could be something in here that you miss.
Yes.
Right? But the point is that you're not always going to go from here to here. You're going to sometimes go. You're going to have an even distribution along that dimension, or even in some
I see.
important sample space.
So it does
right?
sample the
So it
space
will
in
sample
between.
the space in between it, just
Not every time.
every single time.
Interesting.
And so you'll need more samples,
Yes.
but each sample will be faster. Right? And on the balance, it's actually quite a bit friendlier to modern architectures. And
Okay.
on that one, I would estimate that a GPU can get probably somewhere between 500 and 2 billion samples per second.
Wow.
So-
Okay. Okay.
And in that case, actually the most expensive part of it will actually be the random number generator.
Right. Well, I'd imagine so, because that's not going to change. It's fixed. Right
Well,
now.
it is, yeah, you're right. It's not going to change.
Right now, it used to be taking up 3.5% of the total runtime, but
Yeah.
as my total runtime has decreased by a factor of 2, now
It's
that the
starting to
percent
take
now
it.
it's taking 7.5 or so, 8%. So anyway, but yeah,
There's some other random number generators that may or may not be good enough for this, but
would be
you know,
faster.
along down the road, that if that starts becoming a bottleneck, let us know. We can point you at some other things.
Okay.
That there's some people using actually it's called the tiny encryption algorithm.
Okay.
So basically the idea is instead of having basically all a pseudo random number generator is some scrambling of bits in some hopefully non-biased way, right? And so what this idea is to actually, you would take the seed, the cell number, and then encrypt it, which also has the same properties, which is scrambling all the bits, and then that becomes the random number generator, and the tiny encryption algorithm is actually a very short sequence of maybe a dozen instructions, a dozen integer operations that can take that seed and turn it into a reasonably well-behaved random number generator. We've actually are putting all of our sampling in our ray tracing system, in our samples for our ray tracing system. We're switching over to use that because it's faster than big heavyweight things like Mercenary Twister, and a whole lot better behaved than the simple things like an LCG. So,
Okay.
so
That'll definitely be something we'll want to look at as we speed things up. What did you call the technique that probabilistically
I can't remember the name of that paper.
But it's the paper you handed me last time we met. Okay.
So, all right. So, let's return a minute to brainstorming why your answers are wrong. Because I'm gonna claim until proven otherwise that there should not be any difference between
I agree.
1,000 samples per pixel, or 1,000 samples per cell, and 2 runs of 500 samples per cell.
I agree.
And up to and it should be within the limits of
Statistic.
the Monte Carlo, the 1 over n squared.
Yeah. Yes.
So these color maps,
I also have kind of bitmap. It's P color in MATLAB, which is sometimes easier.
do you have an analytic formulation of this
For this case,
problem?
it exists. I haven't solved it, but it exists in Modest for this case.
Because what would be interesting is to look at is to subtract out the ground truth. And
Yes.
And look at the differences.
Yes.
There,
But I'd imagine it's, something like this on the left.
yeah, I know that, but I can't do it in my head.
Yes.
A minus.
A minus. Yes. Okay.
So I think it would be.
So what we're looking at is first, second, average of 2, and then I didn't show all 5 independent runs, but average of 5. And you're right, it should. And here we have on the top right is 5,000 rays per cell, which
And-
should be identical to bottom right here.
Yeah, so can you switch back to the?
Yeah.
So one minor comment for sanity in the future is the color map scales are different between those. So
You're
the-
right.
so-
It auto scales
It auto
between
scales.
lowest and highest, and I need to stop
Yeah,
from
fix it.
auto
Make
scaling.
it not do that, and make sure that both ends of the scale are the same.
Yes.
So what's the scale on the other one? This one?
It's
0 to
all
9 was 1 to 0.
one goes
Like
0 to
2 to
10.
10 and
0 to
one's
10 is
3
the
to
most
9.
extreme, and the lowest extreme is 3.5 to 9.
Oh.
A small difference, but it makes so you can't compare them.
And I doubt that's the reason
Yeah.
here, but it's
Still annoying.
You should rule it out anyway. But the
That would actually make
What
this one look
what this
smoother,
is
though.
what this is saying is that when you average things, you get rid of the extreme values.
sure, but
The
multiple
Monte
samples
Carlo
is
should
is
do the
still an
same.
averaging process, right?
Yes.
So it's-
yeah, you're right. We're on the
It's-
same page.
It's an associative operator, and so it.
These should be identical. The bottom right one here and the top right one here should be identical.
So what you might want to do is just pick one of these cells, or 5 of these cells in different regions, and draw or make a graph of the value as you add more and more samples. Right? So just instrument your program to write out, here's the current average.
Sure.
And then, as you do, for I equals 1 to 5,000, dump that out to a 5 and put it up on a graph.
Okay.
It should be converging to the true
To
value.
the true value.
And
And you know what the true value is from the analytics.
From the
yeah,
analytic.
you're going to want to
yes.
get the true value either from the analytics or you could just assume that the this DO's finding is the true value. Either one of those is reasonable. The only place where the discrete, in this problem, the only place where the discrete ordinance is likely to break down is on the corners. So just
Right.
focus
Somewhere in the middle.
somewhere in the middle. So, because it is, so I would suspect that there's some sort of a weighting or bias or something that's not quite right.
Okay.
And that therefore it is,
The random number generator.
It could be the random number generator. I'd be surprised. And
Or-
Mersenne Twister
Or
is
how
robust
you've
enough.
implemented it.
How it- yeah.
Because you could be repeating random numbers. So for this one where you have 5,000, you might be using the same random number multiple
Yes,
times.
so this is a huge problem with WinPy random number generators. That, you know, if you just called rand on your computer, what happens is, you know, after you've done a few hundred of these, it's going to go around and pick the same random numbers, and then it's going to stop converging.
Yes.
Because you're essentially just computing the same answer 3 times in a row. And
Exactly.
So, I'd be surprised that with the Mersenne Twister that you would get that.
It,
So
it claims its sequence before it repeats is like 10 to the 30th. So yeah, I don't think that's the case.
But is it possible that you're using them once
Sure.
once it gives you
I-
the numbers that you're?
It could be.
Yeah.
Yeah.
It could be, but I think Mersenne does the right thing unless you try hard to make it. not too
No, I mean
different.
we're saying gives him the numbers, and then once he has them, he's reusing.
But
them.
Mersenne just has give me an next random number call,
I
right?
call it every time.
You call it.
Yeah, I
So-
call
so-
it every time.
And,
yeah.
and the way that Mersenne Twister works is it fills in 1,000 or 10,000 or something random numbers, and then it just gives you the next one. And then when those run out, it goes and generates a bunch more.
So it's really fast
so
for 1,000, and then
So
it's
you're
slow.
correct. You should look for that, but I'd be
surprised
I can't figure
why
out
why
how
we
you
would do that. But also you can look at so that sequence that goes up and down and then smooths out. You can also look at the convergence of that, and it should be 1 over
N
n
square.
square over the cube of 1 over the square root of n. Right, and so you can see which one is not converging right. This one where you have 5,000, or the one where you do it.
Yes, and that will show
The-
me that
the
this one's
five
not
of
converging
5.
right. But you're right. The
Or it might not. You might be for some reason getting incorrect smoothing on the other one, which
well,
may also
Yeah.
be. All of these reasons seem unlikely, but
Well,
it can
then-
at least tell you which.
5 to 15 doesn't even look like it's converging.
right.
either.
Right.
I'm kind of approaching this as.
it looks like it's I don't think it 5 to 15. So 3 times the number of samples should be approximately square root of 3 better, right? And so that's the other comment that you should if you can find the true solution, draw a graph of the RMS error over the whole domain, and the RMS error should go down by 1 over n squared.
Okay.
And so between 5 and 15,
1 over the square root of n.
eyeballing it, I would say that the RMS error didn't go down. So, but it's hard to tell.
Okay.
So one sort of word of warning with Monte Carlo algorithms in general is they're really good at sampling the entire space. They will also sample the entire space of your program, and they will find every bug, every single one. I've had programs where worked fine for years, and then we turn on some Monte Carlo thing, and it's, you'll find several bugs.
So take it out of Uinta, is that what you're saying?
Might want to, but
By finding bugs, you mean it won't run, or will run but incorrectly?
user run it incorrectly. So so if your marching isn't quite right, or if you have some subtle combination of 3 factors where you accidentally step out of the domain in some rare case, it will find that case.
Because you're sampling so
Results.
much of it.
Yeah.
You're exercising all of the code sometime or other.
Yeah.
And so those are the most common mistakes are how you sample from one cell to the next, and how you handle the boundaries.
Okay.
So
Okay. Yeah, and I'd be happy. It'd be great if you could look over the code too.
okay.
We're running short on our time. I have a question on something that will come up as I incorporate scattering and diffuse walls.
Yeah.
all of the equations.
So this is no scattering, it's just emission.
No scattering. Well, yeah. So this is, it handles multiple reflections. It has participating media in that the media has absorption and volumetric emission. And then I trace array until it reaches some threshold value. Right now it's like 0.005, and then I stop tracing it. And eventually I think I'll switch to Russian roulette. I think that's what Paula did. Anyway, because I have a cubic domain, and this would even work in a rectangular domain, in order to take advantage of that knowledge to get my code to run as fast as possible, I used tricks that only work in a Cartesian coordinate system. The problem is all of the equations for diffuse reflections and for scattering are in a polar coordinate system.
All of the equations, what do you mean? You mean the test cases?
The physics, so the way that we implement, the way that we solve for a direction change.
But it's
is-
only polar with respect to one sample point, right?
That's true.
So you can't have a polarized copy of every single thing.
Right. So here's one major
So
difference.
yeah, you have lots of trick to do.
Yeah, exactly. Here's one major difference. Now, because I kept Cartesian coordinates, reflections happen in a flash, because
Yep.
all I have to do is reverse the appropriate direction of the XYZ of the vector. Right? All I do is
because you assume that they're axis aligned. Yeah.
That's right. So this is one of the reasons why I think Paula's code was slow, is because she had to do all this trigonometry for every time she had a reflection, and she was also doing trigonometry to figure out how the distances of her cells. It was more difficult. So
yeah, I mean even so you don't have to do trick to do reflections.
I don't in mine.
Even
Even
if it's
polar?
not axis aligned. So in polar coordinates, who knows what happens?
She's
She
adding
wasn't doing polar
pi.
coordinates.
I thought she was.
And she still had a discrete domain.
Right. Her domain was still, Cartesian. But the way she was, for instance, when I shoot out an array, I pull 3 random numbers. Well, 6 really. I choose a random location within the kernel cell.
Okay.
So that's 3. And then I choose 3 new random numbers, and that gives me a vector, a direction vector.
How?
X, Y, Z.
Okay, so that's probably why your answers are wrong. You should look, because that's not the right way to do it. Because
Okay.
what you've done is you have generated a random number within a cube, and let's talk about it in 2D, right?
Okay.
So you've generated a random number within a square,
Okay.
and then you're projecting that to a circle. Okay, and so you have a uniform random number within a square, and then you project those to a direction, right? In this case, a circle, an angle, right?
Mm-hmm.
Okay.
And then what happens, you can sort of visualize it. There's going to be a lot more clumped up here where the corners are. Just
Mhm.
like if you took a square piece of Nerf ball and shoved it, right? You can imagine the square parts being more, the edges of the square being more dense than the
Yes.
center parts. And so what you actually want to do is generate. There's 2 ways of. This is actually one of the interview questions we ask.
Really?
I just failed.
I just failed. Not getting hard in the video.
There's actually we actually only do it in 2D. There's 2 ways to do this. Actually, that's not true. There are probably a dozen ways of doing this, of which maybe 3 of them are good ideas. So one way to do this is what's called a rejection method.
Okay.
So what you do is you generate the random number within a sphere like you're describing, but
Cube
then
or sphere?
in
In a
a
cube, that's what he did.
Yeah, it's a random number in a cube like you're describing, and then if the length of that, if x squared plus y squared plus z squared is greater than 1, you throw it away and try again.
Okay.
Okay, so what that will do is it will generate a uniform distribution within a sphere. And then you
Yes.
can normalize that length
Into a
to
cube.
project it to a direction.
Okay.
And that's by far the most straightforward way of doing it.
Okay.
There are also there's also another technique actually only requires two random numbers. Is you generate a cosine weighted sample on a disk.
Okay.
So you generate an angle and then a cosine weighted distribution, so there's more in the middle, and then you project that disk up to the sphere. And I can send you the code to do that. It's about like 4 lines of code or something.
Okay.
It's and that's probably, aside from the fact that it has to do some arc cosines, probably or I guess it has to do sines and cosines. Still probably a reasonable way of doing it.
Okay.
There's other techniques. So neither of those techniques preserve stratification very well.
Okay.
So again, if we talk about step 5, 6, and 7, stratification is going to be important down the road, and so so for example, if you say I want 100 samples in a box, instead of picking 100 random samples in a box, what you want is actually a Poisson distribution, so none of the samples get too close together. So you can try it in one of these graphing programs. Just take 100 random samples, and a lot of them will be clumped together, right? You'll get, a couple of them are really close, and big space in between. But what's substantially better is, well, there's various forms of stratified sampling, like whole books written on it. But the most straightforward one is to actually divide the domain up into a 10 by 10 grid,
Okay.
and then pick a random point within each of those grids, which each of those
Yes.
sub-cell grids.
So it's still a random number, but within that grid, so you get.
But
This is the idea of stratification.
Yeah, so it'll be stratified throughout the cell.
Okay.
And so, so then you get bonus points if you stratify it in the 5-dimensional origin and direction space.
I see.
So
I see.
So you want it also to be stratified in those other dimensions as well, and that's the trickier part of how to do a stratified 5-dimensional thing. And it's not that hard. So
Okay.
sometimes what people do is actually warp squares and do all sorts of crazy things.
Okay.
So so we found one bug.
Yeah.
So try
that's
fixing
good.
that. I'm not sure.
And you're right.
It's not going to affect that convergence rate. It would just affect the answer. So
It makes sense. Now that you've drawn the picture, it makes sense. Because if you pick 3 random numbers, wow, cool. You pick 3 random numbers and make that a vector, you're right. That's a sphere. But I'm within a cube. You're right. Yeah, it's things like this that you don't think of. So it's good that we have you, Steve.
But I think I derailed you on describing what you did. So you pick a
Okay.
point, you pick a direction,
Yeah.
that you normalize that, and then and I was trying to remember the point you were in the middle
What
of
was
trying
the
to make.
point I was? About diffuse.
Correct.
Diffuse and scattering.
All right. So at each point in that dimension, at each march through the cell, you're computing an absorption and an emission.
That's right.
And so there's no change of direction.
That's right. Right now the only thing that's changing the direction is reflections.
Okay.
Okay. Which works great in Cartesian coordinates with a cubic domain. So my question is it going to be a problem if I'm having to switch to polar coordinates all the time when I am computing a new direction after scattering or diffuse
Yeah.
reflection?
You are most certainly going to have a lot of trig going on, but don't think about it in terms of polar coordinates.
You're right, it's trigonometry, because what I'm doing is I'm switching from, Cartesian direction, I'm converting to R kind of thing, finding the R and then finding a theta. Yeah, so
So, yeah, you probably won't ever, you'll rarely need the angle, because the measure of, so in a vector space, the measure of an angle is a dot product. So if you have two vectors, and you dot them together, so A dot B is actually the magnitude of A times the magnitude of B times the cosine of the angle between them. And so in let's say 85% of situations, you can substitute a dot product or sometimes a cross product where you would normally expect to have to do some trig. And so for example, in a reflection, you can compute a reflection off of an arbitrary surface if all you know is the normal.
the normal, that's right.
Right? And so it's so if you have some incoming direction, we call it V, then the reflection, the angle of the reflection, you could compute angles between these and all that stuff, and you'll be here a long time trying to figure that out. But it's actually just V minus n times 2 n dot V. And we can derive that at another time if you want, but it's just going to be a dot product and then a couple of vector multiplications. Okay.
You have got to go.
Hello?
Phil, how
Okay.
complicated are we
All right,
going to
thanks.
make
Bye.
the domain in the end? Are we going to do tubes through the walls of the domain eventually?
Uh-huh.
Okay.
So
Okay.
another good benchmark for this is that's also really easy to do in a Cartesian coordinate is to do an infinitely repeating domain. So if if a ray leaves on this side, you bring it around and start back here, and that should. I know what the analytical solution is. It's a constant, right? It should be
Right.
flat everywhere. It's like an
Okay.
infinitely large domain.
So
And
that's
so
a
that's
test.
a really good debugging case.
Okay.
It's also those types of boundary conditions are also useful in
Lots of places.
in lots of situations. You're essentially reducing the dimensionality of the.
Sure. In that case, how would I define when array ends? I just make it the same for every
You
array?
have to make something up, but so Russian roulette would work fine in that situation,
Okay.
right? Otherwise, you just you can compute some maximum distance or whatever, but and live with the bias, right?
Yeah.
So there would be bias if you cut it off, but if you make it small enough, it will still be good enough for the test case.
Okay.
You gotta go, Steve.
Yep. I'm overdue for two things actually. So. But
This has
yeah,
been great.
Let's
We
do it again.
appreciate it.
So dig into some of these things.
Yeah.
And send me your code. I'll take a look. Maybe next week. I'm actually in Europe next week. But
no time constraint on when you have to look at the code.
all right. Thanks.
Yeah, thank you very much. I'll see you later. We'll be in touch.
Yep.
You don't need to worry about non-coordinate aligned surfaces now.
Okay.
I mean,
Okay. Okay.
because often we will deal with those as stair steps anyway.
Okay.
So,
So it's okay to keep my direction vectors Cartesian.
right.
We can do the trig when we need to for the diffuse reflections and the scattering.
Right. He was just giving you that as an example, even on the reflection.
yes.
To deal with your diffusion question, your diffuse surface question.
But it'll be similar for scattering.
It'll be similar
Similar for scattering. Yeah. Yeah. Okay. Well, good.